All right, so we have learned until etching last week. So we've covered so far. If you talk about the semiconductor processing, the main one, so we have already learned about thermal oxidation, lithography, so etching. So now we're going to learn about diffusion process. So if you look at the CMOS structure, so where you have a gate on, and then you have a very thin gate ox layer under the gate. Then you have the silicon as the substrate. So you also have source and drain to form the channel for the MOSFET. So to date, we have learned about the patterning. So we know how to pattern the oxide. We know how to pattern the resist. So basically now you have got your gate on your pattern oxide on silicon. But we still don't have the source and the drain on the left and on the right hand side of the gate ox, below and right and left of the gate ox. So now we're going to learn this process called diffusion in order to do the process. Right, before we move on, let's recap a few things about etching process. So let's go to the first one. Describe wet etching. How do you describe wet etching in this question? What are the main keywords you need to include in your answer? Anyone? Wet etching? I'm Natasha. Will you unmute yourself? How do you describe wet etching? What are the important points you should include?
Wet etching.
Wet. When we talk about wet etching, so what should be in the answer? You can mention the main keywords, okay? Tak perlu ada ayat yang
Isotropic.
Isotropic, okay. Are they all isotropic? Are they all isotropic, the wet etching process, or you also have an isotropic wet etch?
No, isotropic.
Just isotropic.
Yes.
Okay, what else? What else is the component of the answer? When you say it's wet etch, what are the important points that you shouldn't miss? Look at the word there, wet etch, wet. So you shouldn't miss wet, right? Wet chemical, right? So you use a liquid chemical because it's wet. Okay, lagi apa lagi? Wet etch, isotropic is it, and what else? Ada anyone else nak tambah? Faika, what else should include in the wet etching description? Highly selective, yes, highly selective, right? Apa lagi? Then you can actually divide, or you might want to explain what do you mean by liquid chemical, what are the examples of liquid chemical. Then when you talk about selectivity, what sort of selectivity do you mean? So give examples of selectivity of certain chemical towards silicon and so on, right? You can also describe isotropic. So what does it mean? What are the examples of chemicals that can do isotropic? So if there's anisotropic as well, so what are the examples of chemicals for anisotropic and how does it look like as far as the textures or features on the surface is concerned? Right, done. So next one, describe dry etching. The other one, the opposite one. So what should you have? What are the important words? Inas, what's dry etching? Plasma, yeah, plasma, good. Dry etching uses plasma. Lagi? Apa lagi? What else can you say about? Just use the very same component we have discussed on the wet etch, and then do the very same thing to the dry etch. Anisotropic, yes, anisotropic. Give examples where you have vertical etching of the plasma on the silicon or on some other structures in order to remove, in order to do patterning, perhaps to finish the lithography process. Any other thing? When you say plasma, where do you get plasma? Where do you set up the plasma? How do you even get the plasma? Can you get plasma at atmospheric pressure? All right, ionized gas, great, ionized gas. So can you get ionized gas at atmospheric pressure? Put it up. Can you get at 1 atm, 760 to 1000 millibar plasma? Is it possible? Or you should be doing that in vacuum? Pull it up. Isn't it vacuum? Yes. Most commonly, well, common cases we get our plasma in vacuum, but there's a case where you also can get your plasma at atmospheric pressure. So we can call it atmospheric plasma system. Tapi usually the common system kita pakai vacuum lah, down to 10-5 torr, for example, and then you inject your argon, then initiate the plasma formation, and then you get the plasma inside vacuum chamber. Tapi ada case yang you boleh pakai atmospheric plasma dalam plasma at atmospheric pressure. Right, we have that system in our lab. We call it APCVD, atmospheric plasma CVD, chemical vapor deposition. We will discuss that when we talk about thin film deposition in maybe next week also, or maybe the other week. Right, done. Wet etching can either be isotropic and anisotropic. So we've discussed this one during the first question just now. So give an example of isotropic wet etching and also another example of anisotropic wet etch. So what does it mean by isotropic wet etching? Before you give examples. Fazira? What is isotropic wet etch? Fazira? Aniza ada? What is isotropic wet etch?
Isotropic.
Okay.
The same rate in all directions.
Yes, good. Same etching rate in all directions. Good. So you're gonna etch the whole features, all angles with the same etch rate. Whereas for anisotropy, you're gonna etch different angle or different planes, more specific, with different etch rate. So give one example of isotropic wet etching. Aniza etch in multi-direction, yep, but with equal etch rate, okay? The answer, you should complete that with equal etch rate. So what is the example of isotropic wet etching? Give me one example. HF, right? HF is one isotropic wet etch. So how about anisotropic wet etch? One example. KOH, TMA, NaOH, right? So if I have a silicon planar silicon wafer, and then I put that wafer in one bath containing HF and HNO3 usually. So what do you get on your surface of the silicon? So you ada planar silicon, you masuk dalam isotropic wet etchant. So you leave it for like few minutes, for example, then you pick it up, and then what do you get on the surface? What sort of features do you get? Usually for HF plus HNO3. No, not pyramids. Pyramid will be in the anisotropic case. Right. Inverted itself, either inverted or upright pyramids. Let me draw here. Okay, kalau you cakap pyramids, so this surface is originally a flat silicon. Ni flat silicon lah, yang awal-awal ni kiranya flat lah. But then if you talk about pyramid, so that means these portions have been removed during the etching. Right, to be able to get these areas, the shaded areas removed, you need to get anisotropic etching. Barulah you akan dapat feature yang ada bentuk. Kalau tidak, you akan dapat bulat je lah. Right, bulat mean isotropic, right? You said Fazira, circular shape or micropore lah, macam lubang bulat. But then for anisotropic, you're gonna get pyramid features, either upright or inverted, depending on the chemicals. Because for this particular pyramid etching, 100 is etched a lot faster than 111. Right, 100 is etched a lot faster than 111, the plane. So that's leaving your pyramid face as 111. Sebab dia punya etching tak sama lah. So that's why we call it anisotropic. So for isotropic, on the other hand, you're gonna get something like this. You're gonna get something like circular pore, bowl-shaped pores, because the etching direction in all directions are equal, right? Equal. Whereas for this is not equal. This one is the slowest plane, 111. Right? So what is this? Hazika, can we do conclusion? The anisotropic, we use alkali solution, isotropic. Yes, exactly. Right, you pick that up. Yes. Usually for isotropic etching, we use acidic, or we call it acidic etch. For anisotropic, we use alkaline etch. Exactly, good. Right? So that's how it goes. But in some cases, where they are not within this pyramid or the pore thing, you can also use some combination of both to be able to get special features. Okay, tapi ini yang very clear cut lah, pyramid ataupun pore shape is very clear cut. But when we talk about some other features, maybe you need a combination of here and there, and you don't really fall into either distinct category anymore. Okay. So the final question, why RCA cleaning is important in IC fabrication? Why RCA cleaning is important in IC fabrication? What is RCA to begin with? Shahira? What is RCA? Shahira ada?
Nak
Ya, sila. What is RCA? Ya, saya dengar. Go on. Tak clear ke? Syah? It's okay, ada line problem kot. Amira? Anything, Amira? What is RCA?
Ya, Doktor.
Yep.
Sorry. Problem. Line. RCA means
Apa,
Radio
it's okay.
Corporation America.
Apa, sorry? Radio?
Radio Corporation America.
Yes, good. Radio Corporation of America, okay? So, okay. Apa, it's okay. Line trouble is fine. So, right. Why is it important then? If you can continue, ataupun if you can't, then some other students. Why is it important? What are we doing during RCA? That is so important. Anyone? Amira, would like to continue on that? Apa yang kita buat during RCA? Remove unwanted materials, right? Great. So what are those unwanted materials? How many steps of RCA do we have? 3 steps, right? So what's the first, second, and the third? What do we remove? So we have 3 steps for 3 different purposes. So what do we remove? Organic contaminants. Yep, organic contaminant, native oxide, and heavy metals. Good, right? So to be able to start your process, you need to remove all these 3 first. Then only we can start with the thermal oxidation and the rest of the processing. Right, let's move on to our topic for today. All right, so introduction to diffusion. So we want to fabricate our source and drain for this particular CMOS feature. If you talk about CMOS, if you talk about some other devices, it depends on what sort of doping do you have, how do they look like, I mean, in terms of the area, is it isolated areas like source and drain for CMOS, or is it just like a blanket surface of single polarity as for solar cell? You may have some different architectures as well if you talk about lasers, diode, and stuff like that. So for this particular case, we're going to look at IC to be more specific, but the very same knowledge can be used for some other fabrication of semiconductor devices as well. So if you talk about IC, so impurity diffusion is a process of incorporating dopants, either p-type or n-type, into silicon, because we talk about silicon as the host lattice. So as far as silicon is concerned, to be able to make it more p-type, you need to incorporate, or you need to diffuse group 3 periodic table, or you need to incorporate group 5 F dopant S dopants in order to make it n-type, right? So the role here is to control type of majority carriers. So we've learned about majority carriers in 386 last time. So majority carriers means the type of carriers that dominate the device or the semiconductor material, and it's given by, if you want to calculate at a thermal equilibrium, you can calculate that by NP equal Ni squared. So you know the Ni for silicon, 1 times 10 to the 10. If you know the majority carrier, you can come out with the minority carrier as well. So 10 to the 20 divided by your one carrier to be able to get another carrier. So you can control the majority type of the carriers in your semiconductor material or device. So controlling majority carriers also means that we are controlling the resistivity of that particular area. Either it's a blanket surface, or it's a specialized regions like the one that we see here for source and drain. So it can be isolated region here. In some cases, you can also do diffusion where you have, say you have this one p-type silicon, you can also diffuse n-type here using phosphorus blanket. So this is particularly for solar cell, but the one that we were talking about now is for CMOS, right? So next, so every semiconductor device depends on ability to fabricate well-controlled, locally doped region of impurities. So in fact, if you talk about solar cells, there are some cases where you also have to introduce heavily doped region. You can go back to the previous page. For example, if you have something like this, n-type, so the p-type is typically around 1016, the n-type is typically around 1019, but within the n-type up there, you also have some heavily doped region as well in isolation. So you may have the blanket dope to be 1E19, for example, but this one may go up to 7E19. So just in isolated region. So if you talk about, if you discuss about solar cell, you will understand why do we need the heavily doped region. It's more of the improving contact resistance between the top emitter N-type with the metal contacts later on, so that you can easily get ohmic contact formation, less resistive, and you're going to reduce the overall series resistance of the emitter and the emitter to the contact in order to improve solar cell performance. But for this particular case, if you talk about CMOS, so it's a completely isolated region of p-type, for example, in this page. So tapi keliling ni semua n-type, right? Or you may have the silicon to be p-type, but your source and drain can be n-type, tapi tak ada n-type yang lightly doped. So that's why I say the fundamental knowledge is the same, but the moment you go for your devices, so it depends on your device architecture. Either it's blanket or heavily doped in blanket or heavily doped in isolation. It can be entirely different cases for different devices. In fact, if you talk about the very same device as well, if you have a range of product, if you have a range of technologies in the industry, you may have different architectures as well, even though they are one LED as a device. But then you talk about LED A, LED B, LED C, some might have slightly different architectures depending on the role of the final device. Just like what mentioned by Dr. Fabian last time. So he said that if you are fabricating simple device, so you may take like 2 weeks maybe. So if you're going for more complicated devices, you may take slightly longer, like 3 or 4 weeks. So it depends on the device architecture that we're talking about. So bottom line, we want to fabricate well-controlled dope regions, either blanket or in isolation or in whatever configuration. So we want to introduce impurities, and impurities in this case are desired impurities. Kalau you nak recall balik 386 last time, we had discussed about desired and undesired. So in this case, it's desired impurities because you want to introduce the dopants into the silicon lattice. And you want to change the electrical properties of your silicon eventually to follow certain rules or certain, operation, if you like. Okay, if you look at this figure down here, you can actually zoom out a little bit and you can see a silicon on the right. So it's actually a silicon flip 90 degrees anti-clockwise, and this is the surface of silicon. So the surface of silicon in this case will be at the origin of the graph on the left. So this will be representing the surface of silicon. So if I can draw the very same silicon on the graph, it's going to be something like this, more or less. Sama macam saya drawing on the right. So surface will be on the left, facing, it'll be sitting on the y-axis if you like. So the y-axis for the plot is the concentration of the dopant. So if you're talking about p-type silicon, for example, kalau you use silicon p-type, so you want to dope n-type into the surface. So maksudnya you punya profile ni, semua ni profile ni, semua n-type lah. So n-type can either be a phosphorus or arsenic or antimony, and the typical one is phosphorus, of course. So that profile belongs to n-type, and your wafer is p-type. So eventually you want to have something like this, for example. Contoh, it may be just a localized region, tapi saya just draw blanket. So eventually on the wafer, you're going to have something like that physically. And a very thin N layer on a p-type silicon. That silicon thickness may be, I don't know, maybe 300, 400 micron thick. And the dope region is typically less than 1 micron, depending on the device configuration. Some might need a very thin one, some might go with a very thick one, depending on what is it for, right? So in this particular case, you're going to have a doping profile like that. We're going to see why later on. And then this value here is actually your bulk concentration. Bulk concentration tu maksudnya you punya doping level dalam p-type. So it belongs to p-type, right? So kalau if your wafer N-type, then the bulk concentration will be your N-type. If your wafer is P-type, then your bulk concentration will be your P-type. So in this particular case, if you look at the value on the y-axis, so it's somewhere 10-15 as your bulk concentration, right? So tapi you punya profile, when you dope, you're going to get something like maybe 5E19 here, maybe 5 times E1019. We're going to see the details later on. We need just contoh, yeah? And that is normally called as N0 or peak concentration. We call it N0, right? So, and then it's going to have a profile like that. We're going to see why later on. So basically that's how it looks like if you do a cross section of your wafer after diffusion process. And now we're going to learn on how do we actually do that. All right, so we are talking about silicon as our host lattice. So silicon is group 4. So to be able to make it p-type, you need to dope group 3. To be able to make it n-type, you need to dope it using atoms from group 5. P-type, huh? So p-type, n-type. Right? P-type, n-type. So p-type usually can be boron, aluminium, gallium, but the most common one is boron. The very same thing happens in solar cell industry as well. We use boron for p-type, and we use phosphorus for n-type. So this one is a common one. Tapi you boleh juga pakai others. For example, if you talk about Silterra, Silterra has boron in diborane gas, in the form of diborane gas. We have phosphorus in the form of phosphine, pH 3. There's also arsine. There's also phosphorus pentachloride or trichloride. So it can be different forms. But the most common dopants for group 3 is boron, group 5 is phosphorus. So atomistic model of diffusion, the dopants or the impurities can be incorporated into the silicon lattice by 2 ways. So it can either be by substitutional or by interstitial method. So if you look at the examples of elements for substitutional, the method number 1. So usually phosphorus, boron, arsenic, aluminium, gallium, antimony, germanium, they are incorporated into the lattice by substitutional method, where they actually substitute the host atoms in the lattice. Interstitial, on the other hand, oxygen, gold, iron, copper, nickel, zinc, magnesium, where they form an interstitial site beside the atom. Dia duduk kat tepi, dia tak replace tapi dia duduk kat tepi. So that is interstitial. So this is how it looks like. So you can see that it sits beside the host silicon atom. So silicon is the interstitial atom, displaces a substitutional impurity, driving the impurity to an interstitial site, duduk kat tepi, where it diffuses some distance before it turns to the side. Okay, so that's how it's incorporated into the lattice. So to be able to do this, to be able to incorporate the impurities or dopants, in this case, either by substitutional or by interstitial, there are 2 processes that we normally use called diffusion. The first one is diffusion, and the second one is ion implantation. So we're going to learn diffusion this week, maybe a little bit of next week, and then we're going to continue on to ion implantation, which is another way to do incorporation of impurities into the silicon. Or in reality, for example, if you talk about IC fabrication, the chip may require a combination of implantation and diffusion at different steps in order to realize the formation of the dope regions on the device. So it's not necessarily purely diffusion or purely ion implantation. It can also be a combination of both. If you talk about solar cell fabrication, usually just one process is used, which is called diffusion, because diffusion is a lot easier to do and cheaper in terms of cost in comparison to ion implantation. Ion implantation dia lebih mahal. You're going to need ion implanter. You need to accelerate the precursor materials at high speed. We're going to see later on how does it bend in terms of the root, and then you're going to attack the surface of the silicon at high energy in order to embed the impurity atoms into the silicon. You're going to see what's the difference between diffusion and ion implantation later on. Okay, so diffusion and ion implantation, in principle, this is how it looks like. So, so your silicon and your mass is on the left-hand side. So when I say mass, we have discussed this one last time. You can have, for example, SiO2 as your mass, right? We have discussed when we talk about, when we talk about thermal oxidation last time, where you can actually thermally oxidize the oxide, and then you pattern the oxide by lithography and finish it off by etching process, and then you can then dope the open areas. So sebelum ni kita belajar we pattern the oxide. So why do we pattern the oxide? Because we want to dope specific regions and you want to undope specific region. Sebab tu kita buat mask. Kalau tidak, tak perlu ada mask. You can just have a blanket one and you can't dope anywhere because it is masked already. It's protection already. It's protected already. So the mask here serves as a protection layer. So in this particular case, the regions that you open, you expose. So in this case, dekat tengah ni, is typically the region that you want to dope because it's exposed to the ambient, right? So that means your impurity can come in and dope the region. So in this particular case, if you talk about diffusion process, so below you dope, that's how it's gonna look like. You can see the shaded region here, or the dotted region if you like. So the region is somewhere like this. Lebih kurang. And the profile, if you look at on the right hand side graph tadi yang kita tengok y-axis concentration, x-axis depth, you can flip it 90 degrees clockwise now. So your ln C is your concentration. So this one will then be your N naught, macam tadi saya draw tadi. So you flip it 90 degrees clockwise, and X is your depth into silicon. So X0 is the surface of your silicon. Then you're going to increase your X into the depth of the silicon. So if you plot the concentration, it's going to look something like that on the right. So kalau you pakai ion implantation on the other hand, so you're going to bombard the ions at high velocity, well targeted, you're going to end up with something like this. Anything that you can see, the main difference between ion implantation profile versus diffusion profile. Anything obvious you can see? Apa yang obvious between these two profiles? Sebelum kita pergi ke the actual topic. Apa yang obvious? At least from this sketch. Apa yang obvious that you can see? Cuba compare atas dan bawah, apple to apple. Which one has a wider profile? Diffusion or implantation? Wider means on the X. Kalau tengok dia, yang mana yang lebih lebar? Profile yang you dope tu. Right? Diffusion, right? Okay, so diffusion tends to have a wider profile. Kita akan tengok kenapa. It's actually due to the diffusion of impurities in all directions. So you're going to have, below you diffuse, you're going to have vertical components. That means the incorporated atoms are actually diffusing into silicon. Not only into silicon, they are going also in diagonal direction. They're also going in lateral direction or horizontal direction. So that leads to the formation of a wider profile by diffusion process. On the other hand, kalau you tengok benda yang sama, scope yang sama, so the ion implanted profile is not broad. It's localized, it's narrow, it's well targeted. You can see, you tengok for diffusion, even areas under the mask are slightly dope as well kan? You nampak. Semuanya under the mask, but then they are also doped, right? On the other hand, if you look at the ion implanted, right? So if you look at the ion implanted profile, you can see the areas under the mask are barely doped. Dia mungkin ada tepi-tepi, sipi-sipi lah. But then you can more or less say that they're gonna be doped more or less like that. Vertical, well targeted, localized, less spread. Sebab kita punya ion tu are bombarded at high energy, coming right into your silicon at high speed. Boom. Dia masuk je. So maknanya dia ada minimum deviation. Bila dia datang at high energy, dia ada minimum deviation to the lateral direction, to the horizontal. Dia masuk right into the surface of the silicon, into the bulk of silicon, forming the dope region. So on the other hand, if you look at the diffusion, there's also a lateral component, a bit of diagonal component. Then you're going to end up with a slightly wider diffuse profile under the mask, even under the mask. So if you talk about, for example, kalau you nak dope technology node of 3 nanometer or 5 nanometer that is very close to each other, very packed, are you going for diffusion or implantation to produce your dope region? Which one are you going to choose? Now we're talking about small technology node packed very close to each other. You need a very accurate formation of doping profile. Are you going for diffusion or ion implantation? Ion implantation, right? Because it's well targeted, small area, less broad. So just imagine kalau you pakai diffusion. I'm not saying that you can't use diffusion. You can, but well controlled diffusion. Cumanya bila you talk about small technology node gate yang rapat-rapat, even though they are isolated from each other. So kalau you terlalu small, then even area under the mask pun is also doped, then you cannot control the formation of your channel later on. Okay, so this is the brief of the formation between diffusion and ion implantation. You can also read the summary there. Max concentration for diffusion occurs at the surface, open, diffuse into wafer, but also diagonal and also lateral. We're going to see later on. For ion implantation, dopants embedded. They masuk dalam. You can even ion implant the dopants into the silicon without disrupting the surface. You boleh actually embed the dope region to dalam. You can do that actually by high energy. You're going to see later on that you're going to have low energy implanter, medium energy implanter, high energy implanter to do various jobs during the fabrication process. All right, so let's look at the source of your dopants. Right, source of dopants. So, so if you look at N-type, we have a couple of dopants that we can use: antimony, arsenic, phosphorus, and the source can be antimony trioxide, Sb2O3, arsenic trioxide, arsine. Arsine is typically used in IC fabrication, AsH3. If you look at phosphorus, the most common one is phosphorus oxychloride, POCl3, or we normally call it POCl, or phosphorus pentoxide, or P2O5, or even phosphate PH3, right? So if you look at boron, the source can be from boron tribromide, boron trioxide, dibrane. Dibrane is a commonly used one. In Satara, they use dibrane, B2H6, and arsine, and phosphine, and I think POCl as well, if I'm not mistaken. If you look at solar cell, if you have a P-type silicon wafer, you want to do N-type diffuse layer, they normally use POCl for N-type emitter, a very thin one, like about 100 to 200 nanometer thick for solar cell. So the precursors here in the table can be from various sources. So it can be from solid form, it can be from gas, it can be from liquid as well. So depending on what is the best for your process. So if you look at POCl setup, so this one is POCl for phosphorus, POCl3, or phosphorus oxychloride. So this is the typical setup. It's quite simple. So you have POCl as your source. So POCl is the source. phosphorus oxychloride, then you blow N2. You also have oxide, oxygen gas for oxide formation. Then it's going to be, the poker is going to be under a bubbling condition. So you have to produce bubble. And then the bubble will be sent by N2 gas into the furnace. So the furnace is here. So your wafers are all here. So you're going to have your heater here. So your kind of heater to heat up your chamber. So it's typically done between 900 to 1000 degrees C. So process duration, well, it depends. It may go from like 20 minutes up to 1 hour, 1 hour plus at different temperatures. So according to what you need. And then your wafer, if you put your wafer in the chamber like that, so kalau you ada, for example, katalah you letak wafer ni, wafer is typically placed either vertical or horizontal. So if you have vertical, for example, katalah ni you punya cross section silicon wafer, you ada banyak wafer. So this is your quartz board. So phosphorus coming from this way. So you're gonna diffuse the layer throughout the region. Sebab semua ni duduk dalam ambient, dalam furnace. Usually, the whole surfaces of the silicon will be doped. So you're going to have your phosphorus everywhere, wrapping your silicon. Tapi you nak dekat depannya, for example. So you tak nak kat belakang. So you're going to need to do something else after the process to be able that you are left with only doped region on the front side, the targeted area. Right? So Fick's first law in general is what's governing the diffusion process. We've discussed this when we talk about the growth model last time during thermal oxidation. So you have seen this example before. So where you have oxide, where you have a precursor material crossing through oxide, and then only it's coming to silicon. You have different flux condition at different time, at different thickness in order to form the oxidation process. And the Fick's first law is gives you the equation here, J, or the particle flux that is governing the diffusion process in this case as well, equals to negative d diffusivity times d and dx. N will be your flux, will be your particle, will be your phosphorus in this case, against the depth of silicon, right? So the Fick's second law is what combines the first law with continuity equation. So if you look at this description, the continuity equation for particle flux, rate of increase of concentration is equal to the negative of the divergence of the particle flux, or dN dt. dN dt is equals to negative dj dx in one dimension. So when you combine, you're going to have dN dt equals to diffusivity times d to n dx squared. So you're going to see later on when we use the equation to do the calculation, right? Dose of the precursor material is given by impurities per cm squared. We're going to use this one for calculation later on. Dose is Q. I think when you do the calculation, you will see the difference between two different profile calculation. We're going to come to that later on. Okay, let me finish another few more slides. The diffusion process, forget about ion plantation first. If you talk about diffusion process, it can be done by two ways, right? It can be done by two ways. The first one is called constant source diffusion. So this means when you run your diffusion process, for example, you run your process at 950 degrees C for like 1 hour in nitrogen condition, in nitrogen atmosphere. So what constant source means, throughout the 1 hour, so the whole 1 hour, you're going to have your phosphorus coming in during the process. So here from minute number 1 until minute 60, you're going to have your phosphorus coming to see coming in contact with silicon, right? In contact with silicon surfaces to be able to continue the diffusion process. So maksudnya throughout the process you have constant source of phosphorus coming in. Someone's got like, if you talk about boron, for example, then if you talk about constant source, a diffusion process, you have a constant source over the whole time of your phosphorus or boron coming in contact with silicon, right? So it's going to give you a complementary error function profile. So this profile shown in the graph, profile banyak ni, this profile is called error function profile. And you can only get this if you run constant source diffusion process. So we're gonna see the next one, and you're gonna see the next profile for the next one, right? So if you run this the constant source, you hanya akan dapat a complementary error function file which governs the formation of your profile, right? So in this case, if you look at the graph here, the y-axis will be the impurity concentration. So your N naught will be your peak concentration. So your x-axis will be your depth into silicon. Maksudnya depth into silicon. Macam saya draw mula tadi. So if you look at these 1 and 2 and 3, right? So what is the difference is they are run at the time, moving from left to right. So maksudnya kalau you go from left to right, katalah you run process number 1 at 20 minutes, you're going to get profile like that. The very same process, but you run for maybe 40 minutes, 20 minutes, 40 minutes, you're going to get that profile. So nampak kan dia akan go slightly deeper into the silicon. And 3, maybe you run the process for 60 minutes, then it's going to go deeper into the silicon, and it's going to the right here, right? So that means, but notice that the N naught value doesn't change, even though you run the process longer and longer and longer. So your N naught maintains at the same value, but your profile going deeper into silicon. So in order for you to determine the junction thickness, so kita discuss tentang p-n junction formation kan. So say your silicon is p-type, then you diffuse a layer here n-type. So how deep is your junction here? How deep is it going? So how do you determine that? That's normally called xj, or junction depth. Xj junction depth. So to be able to determine junction depth, you can go back to the profile there. Junction depth will be given by the intersection between your dope profile and the background concentration. Background concentration is NB, so which is given by this horizontal line. And then your dope profile, for example, if you look at the 20 minutes process, so your junction depth will be given at this intersection. You go down to the x-axis, so this is your xj for 20 minutes. So if you look at the 40 minutes process, this is the intersection. So this will be your xj for 40 minutes. So this will be your xj for 60 minutes. So the longer the process time, the deeper the junction is. So that's given by the d times t. D is constant diffusivity times the duration of the process. Either it's 20 minutes or 40 minutes or 60 minutes as an example. And overall, the profile equation is given by this function. It's equal to n naught times error function. ERFC means error function profile. Bracket the whole thing. X is the depth over 2 square root of dt. Diffusivity times process duration, square root, then you're going to get your equation to represent the profile, right? So from this particular case as well, if you run constant source diffusion, you can use this equation to calculate the concentration at any point in the silicon. You can use this equation to calculate the dose in the equation during the process. So N naught will be given by your peak concentration, D is the diffusivity or diffusion equation, and ERFC is the error function of the profile, right? Ini contoh, if you run the process at say 15, 30, and 60 minutes, that's how you're going to get exactly like what I explained. because the dt, the product of dt is increasing to the right. So you're increasing the product of dt to the right. Diffusivity times time, or duration of the process. D is constant, T is increasing from left to right. So you're going to get deeper and deeper and deeper into the silicon. And your junction depth will be given by this. For example, in this case, if you look at 15 minutes process, your junction depth is given by, is about 3.5 micron. Right? Xj is 3.5 micron. So for this one is 5 micron, 7 micron, but we don't go that deep usually, right? Okay, so saya cover satu lagi, Gaussian profile, so that you can see the difference. Then we're gonna stop. So Gaussian profile, on the other hand, is obtained when we run the diffusion process with limited source. Apa maksud limited source? If you talk about constant sources now, that means if you run the process for like 1 hour, you're gonna have your phosphorus coming into the chamber for the whole 1 hour duration. So it's called constant. On the other hand, the second method to run the process is called limited source, where if you run your diffusion for like 1 hour, so you may have your phosphorus coming in for like 20 minutes, and then at 20 minutes, the phosphorus is stopped, no more Pocal coming in. But from 21 minutes until 60 minutes, you're going to have, you will run the diffusion process only with what is available on the surface. Below you have your phosphorus coming in, it will actually be deposited on the surface, and then the high temperature that you have will actually diffuse whatever that you have on the surface into the silicon. But in this particular case, you have limited source for like 15 or 20 minutes. So after that 20 minutes, you only have that much of dose of phosphorus you have on the surface. So you ada itu je untuk you diffuse into your silicon. So that's why we call it limited source. When you run the process with limited source, no matter how long the source is coming in, 15, 20, half an hour, 40 minutes. So you're going to follow the Gaussian profile to be able to do, or to estimate, or to predict the profile of your diffuse atoms, okay? So if you look at a longer time, in this case, D1, D2, D3, DT1, DT2, DT3, so you can see that now if you run your process number 1, process number 2, process number 3, 1 is giving you this way, 2 is giving you this way now. It's going deeper as well, but then what is the change here? Kalau you compare this profile and the previous profile, apa beza dia? What is the obvious difference? What is the obvious difference? Kalau you compare profile dengan profile error function, apa yang paling obvious? Anyone? Any difference to the N naught between Gaussian and error function? Shazwani, any difference? Higher impurity concentration, lower depth. Yep, right, okay. So if you go from process number 1 to number 3, Naim, is there any change of N naught? Is there any change of N naught? Any change from process 1 to 2 to 3? N naught ada beza tak? Yes, N naught decreases, right? So kalau kita tengok error function tadi, you will N naught maintain. If your process time increases, it's just going to go deeper, but without affecting the value of N naught. There's only one single value of N naught because you have constant source. So your N naught is constant throughout the process. On the other hand, if you look at Gaussian, limited source, you supply maybe for like 20 minutes or 30 minutes, then the moment you run the process longer, your source at the surface is going to be depleted. So the longer you run, the longer the more the phosphorus at the surface will be consumed into the surface. Maknanya you akan deplete the value of N naught as you go longer, right? So you're gonna see that your N naught decreases if you go longer, and your profile going deeper. Profile going deeper itu sama dengan error function, but then the obvious difference is error function doesn't have any change in the N naught because of constant source coming in. But for Gaussian profile, you're gonna be depleted of your peak concentration at the surface because you only have limited source to continue the process. So that's why your N naught decreases as the process goes longer. So for this Gaussian profile, you need to use this calculation for this equation for the calculation of concentration, this equation for the surface concentration, and you're gonna need to use the Gaussian profile. You can compare later on what is the difference between equation for Gaussian and equation for error function. So I think I'm just gonna stop here. Then I'll see you again next week with the diffusion process. We have like 20 more slides to go for the diffusion process. Right, do you understand so far? Is it okay? Semua paham? Anything you would like to ask on the diffusion? At the end of this diffusion, we're going to do some calculation. Nanti try tengok juga page. Where is it? Right, try to look at the last page, page 34. Cuba tengok macam mana nak buat calculation tu using the equation that you have learned just now. Maybe we can discuss in the next session after covering the diffusion process. Right, so no questions? All good? All right, so far so good. Okay then. So I'll see you next week. Bye-bye. Take care. Assalamualaikum. Stay safe. Have a nice weekend. You too. Bye.